presentation. I'm very honored to present Dr. Barish, who is joining us virtually in Cambridge. Hello, Professor Barry. I'll just take a moment to briefly introduce you. We have Dr. Barish, who won Nobel Prize in 2017 for his work exactly on decisive contribution to the LIGO detector and observation of gravitational wave.
Okay, I guess it's my turn. Greetings, everyone. I guess good afternoon. For me, it's early morning. I'm in California. What I'm going to do today is to introduce you to a rather new topic, which is gravitational waves. And it's rather broad, so I'm going to cover it several aspects so you can get some sense what this is all about. So I'm not going to emphasize the discovery of gravitational waves, but actually what we're able to do with a new science is opened up by the detection of gravitational waves and what we can anticipate happening in the future. So in a sense, the picture on the left is a graphic showing, I'll talk just very briefly about the technique we use, which is called interferometry, to measure gravitational waves, with a cartoon of what has been detected, which is the in spiral of a pair of black holes that are attracted to each other by gravity. And as they are attracted, they go around and around each other at near the speed of light and eventually merge, emitting gravitational waves, which is what we detected. But before I come to that, I want to kind of put this whole subject into perspective. So I want to advance my slide, but I'm having trouble. Okay. So I'm going to start by talking about the parallel subject, which is astronomy. And we all know the wonders of astronomy, but when we look at the history of astronomy, it's in many ways going to be paralleled by what will happen with gravity, because basically what we've done, other than the physics of seeing gravitational waves, is open up a new way to look at the sky. Galileo was the first one that kind of opened up, let's call it, a new way to look at the sky. And that was the birth of modern astronomy. Before Galileo, there were no instruments that looked at the sky. It was done with the naked eye. And so everything we knew about the universe, the solar system, the sun, came from observations involving basically the naked eye. In the early 1600s, I think 1607, Galileo was aware that the telescope had been invented. He didn't invent it, but he built a telescope. He built a 20-power telescope, and he used it, like the little picture on the left, to look at Jupiter. And when he looked at Jupiter, he saw something that hadn't been seen before because of the 20-power telescope, and that was that Jupiter had 4 bright objects that were near it. And he assumed at the beginning what anyone would have assumed, that that was in his field of view, that that was stars behind Jupiter that were seen there. But he came back and looked a second night and a third night, and these bright objects stayed close to Jupiter and didn't move in the sky as stars would have. And so he discovered the famous 4 moons of Jupiter. We now know there's something like 100 moons of Jupiter, but he discovered the 4 moons of Jupiter. And in a sense, that was the beginning of modern astronomy where we use instruments to study the universe. And we've advanced a long ways in a little more than 400 years. But if you want to pick one thing after Galileo that's made the biggest difference, it's illustrated in the slide that I put up now. And that is everything that was done with the naked eye, of course, and with Galileo's telescope. And the better telescopes that followed for several hundred years was looking at visible light. The big revolution that happened in the last 100 years is to look at objects, phenomena in the sky, but not just with visible light, but with all other frequencies of light. So I show here an illustration of the different frequencies of electromagnetic radiation that exist, where the bottom pictures are kind of the practical uses of them, and above is just kind of the wavelength. And we do the same thing, but to discover features of objects in the sky. So using different frequency different frequency electromagnetic radiation, we vary from creating the radio to making heat and fire, to visible things that we look at, to looking inside the body, to actually radiating and doing things like killing cancer. So having all the different frequencies is a huge number of instrumental ways to do things in nature that we do on the Earth, like I show here, but also to look at the sky. And that power is the main thing that's advanced us in modern astronomy, where we look at the same object. Illustrated here is an object that was a supernova, a remnant of Cassiopeia A, in different frequencies. So you see the images, I'm not going to talk about it, look very different in the different frequencies. One is the X-ray, one is infrared, one is in the radio, and one is in the optical. And using those different frequencies, we're able to study and learn much more than just that we visibly saw some object in the sky. So that's been the biggest single advance, in my opinion, in modern astronomy. As we've entered this century, we've seen another interesting advance, a little bit of a side subject, and that is not just combining different frequencies, but actually combining instruments, which is another interesting feature. So only, 3 or 4 years ago, in this century, a group took existing objects, just like we're doing with, say, gravitational waves, one object, one instrument. They took instruments that existed, shown in the picture of the world on the left, combined them together into their radio telescopes, combined the data together in a way that it acted wherever it looked in the sky like one instrument, but the one instrument which had a poorer resolution, but was the size of the Earth. So we make radio telescopes, usually like the picture in the upper left, about 5 or 10 meters across. This is now a radio telescope, poor quality one, but a radio telescope, basically the size of the Earth, by not making any new instruments at all, but combining the data in a very clever way. And doing that, they were able to see an image for the first time, a black hole, M87, which is a big black hole. You see the image on the right. The figure on the left is just what they had to do this. They took the data from all these different objects. They weren't made to be used together. They had to bring it together, write all the software, and then do the imaging and get a final image that you see here. Of course, that's not my subject today, but my subject is predicated on the parallel between how we've advanced through instruments and through techniques in astronomy, and that will follow similarly for gravitational waves. So now I'm going to switch to gravitational waves. So everything up till this slide was talking about electromagnetism, light or other electromagnetic waves in other frequencies, and the instruments that went along with it. A completely different subject in physics is gravity. Gravity was something, of course, people were aware of also in ancient times, but the first real deep and marked understanding of it came from Newton, Sir Isaac Newton, shown here on the left, who in 1687 wrote a book called the Principia. He spent most of his life working on this book, or the physics that went in the book. And what it is the physics of gravity, basically. He started by trying to understand how objects rotate around each other, the moon around the earth around the sun, the other planets around the sun, and knowing that they're elliptical orbits. That was known when he started. And what he believed, having used calculus and derivations, was the theory of gravity, was the famous formula below, that the gravitational pull between two objects is the product of their masses divided by the square of how far apart they are. And the strength of it is what's called capital G. Newton didn't know what the strength was. And in fact, it took another 100 years before using what's called a torsion balance, the strength of gravity was understood. The big problem for Newton was, does this formula give elliptical orbits? And he spent years trying to prove that, and in fact, basically invented calculus to be able to prove that this formula gives the elliptical orbits that planets take going around the sun, for example. And in order to finally publish the book, he wanted a final check. And the final check was not the elliptical orbits of the planets around the moon, but could this formula be used to predict the orbit of a comet? And it turned out during his period of time, the famous Halley's Comet came into field of view, and he predicted the trajectory of Halley's Comet. And basically, that gave him confidence that not just for the planets going around the sun, but universally, this formula works. And so he called his theory a universal theory of gravity. It's the most successful physics theory ever. It's lasted itself without modification for more than 200 years until Einstein came along. Einstein, which I'll talk about next, didn't disprove Newton. That's not what happens. We have theories in physics. They're able to describe things, but essentially, all theories of physics are approximations. They may describe very well whatever they're made to describe, but in most cases, there are phenomena outside of that realm that it doesn't describe. And we make more advanced theories that both describe what the original theory did and what it didn't describe. So in the case of Newton's theory, clearly it didn't describe relativistic phenomenon and so forth. And Einstein developed a new theory of gravity. Where that came from was that Einstein in 1905 solved 4 or 5 of the most important problems in physics in a matter of months. One of those, of course, was famous E equals mc squared, or the theory of special relativity. The theory of special relativity is what happens when we get near the speed of light and what objects do. The clocks tick more slowly and so forth. And he, after that, added accelerations, not just high velocities, to his calculations. And accelerations are equivalent to a theory then of gravity. It took him 10 years to develop that, but then he developed his theory of gravity. So we went from Newton's theory, 1687, universal theory of gravity, to Einstein's, which is very different in terms of its formulation. It's basically based on a unification of space and time. We call it space-time, one word. If you type that into the last time I did it at least, into Microsoft Word, it makes a little wavy line underneath. So they don't yet know that it's one word in that case. The only discrepancy that existed in over 200 years in Newton's theory of gravity was a slight discrepancy in the orbit of Mercury, our planet closest to the sun, as it goes around the sun. As I show in this picture here, it makes a very kind of elliptical orbit, and that orbit precesses around as it goes. And you can calculate from the sun itself the positions of all the planets, how much it should move. And if you calculate it using Newton's theory, you get 532 arc seconds per century is how much it moves forward. And the observed feature was about 10% different than that. So there's a 10% discrepancy and that's the only discrepancy or the only difference that existed at the time Einstein came along. Hardly reason to develop a whole new, very different theory of gravity. But Einstein's theory of gravity did other things. It explained, and we can see it in this picture here, it explained something that we didn't know by Newton's theory. If the apple falls out of the tree, we say it falls to the ground. And Newton's theory tells us the attraction, and you can calculate it. But in fact, how do we know, or how do we realize that it's attractive and not, for example, repulsive? What makes the gravitational force attractive? Newton doesn't explain that, but Einstein does. So if we look at this picture here, Einstein's theory is based on, I can't go through it obviously, goes based on a distortion of space and time itself. So the presence of the sun, which is shown in the middle here, distorts the features of the coordinate system shown below it, much like if you have a trampoline and you put a bowling ball on the middle of it, it'll distort it. And that makes the Earth that's shown there slide to the lowest potential or be attracted to the sun. And the same way as if you put a bowling ball on a trampoline, a marble on the end will roll, put on the edge will roll toward the center. But if there's no bowling ball, it won't move. So basically, Einstein added one thing just by having his new theory, and that is why gravity is attractive. A second feature that Einstein solved that Newton was aware of, actually, the attraction and repulsion question Newton didn't address in his famous book, The Principia, but this question he mentions, and that is he wondered, or he recognized that when the apple falls out of the tree, the observer can't possibly see it immediately. There's some problem of how long it takes the message to go from the apple to the observer. And he mentions that, kind of saying, and he calls it, his theory is instantaneous action at a distance. So there's action at a distance, but you sense it instantaneously. But as we know, it takes some time for a message to get to you. An example of that I show here. If the sun were to disappear right now, it's a little late in the day for you, so maybe it's gone. But if it just disappeared, it would take 8 minutes before we knew it here on Earth. And that's because the signal, it travels at the speed of light, and it takes 8 minutes to get at the speed of light from the sun to the Earth. So using Einstein's new theory, it made a new prediction, and that is that as an object gets near another object, it's attracted. And it doesn't matter because it's based on the curvature of space-time, not the mass of the objects, like Newton said, that even if the object is only light, it'll get affected by the curvature of space and time. So he predicted that if light were to graze past the sun as it comes to the Earth, it would bend as it went by the sun, and he calculated how much. And then he said there's a way to measure this and measure it when the sun is having a full eclipse and the stars that are further away than the sun go behind it. You should be able to measure that the light from those stars that are behind the sun bent as they came to the Earth. Sir Arthur Eddington, who was actually Arthur Eddington when he did the experiment, measured and proved that. And that was the realization that Einstein had predicted something new. And that is his theory of gravity, or general relativity, as otherwise it's called. As often happens in modern physics, when we discover something new, like the bending of light that I just showed, it then becomes a tool for future research. So in this case, it's a very good example of that. In astronomy now, one of the very powerful tools is what we call gravitational lensing. And it's basically shown in this picture here. If I'm sitting as an observer on the Earth and there's an object that I want to study, it acts as a lens to focus the light that comes from a source that's behind it, just like the light that grazes the sun. And if this object that I'm showing the lens is unknown, we don't know what its features are, we can calculate them from what basically happened to the light that came as a source. We call that gravitational lensing. And examples of that I'm showing on the right, that you can see the grazing on the one on the right, and the most famous example that can almost be seen with the naked eye, but with a small power telescope, usually in the southern hemisphere, is called the Einstein cross. It has a complex set of stars behind it that makes the cross-like picture. So now let's go on more to general relativity and gravitational waves and what we might see in the future. So first, let me point something out. We're often asked as physicists, what's the use of what we do, and does it have any effect on anything? And we struggle to tell them basic research has made many discoveries that are used all the time. I mean, discoveries like the laser, discoveries like stimulated light that is what makes the laser, and so forth. But interestingly enough, even in modern physics, things that are very abstract often have a very large effect, including general relativity. General relativity is generally the last class given in advanced physics for graduate students. It's the hardest class in detail. And yet it's had a big impact on your lives, my life, and every day, because the GPS system that we use in our iPhone or wherever we use it in our car to get us around needs GPS to work, needs general relativity to work. Let me show you why. In special relativity, first, because of special relativity, the way the GPS system works, there's 24 satellites going around. They're going around the Earth at about 14,000 kilometers in height, and they're going fast enough that there's a relativistic correction. And when we study relativity as an undergraduate or graduate student, we learn a little saying, moving clocks tick more slowly, which tells you the sign that if you look at something that is moving fast, the clock goes slower. And so we can calculate that correction, and it's 7 microseconds per day. And actually, in the GPS system that we use, that correction is made in the satellites themselves. So that correction is made in the electronics in the satellites. We send the signals back and forth, and that works. But general relativity, which is what I'm talking about today, also has an effect. Because the satellites are further from the Earth than we are, the amount of gravity is only about 1/4 of what it is on the Earth's surface. And in general relativity, clocks tick faster, not slower. And that correction is bigger than the special relativity correction. It's 45 microseconds per day with the other sign. And if you put that all together, those corrections are both made, and that's why you work, that the correction is 38 microseconds per day. It's made electronically, so you never have to think about it. But if you do a calculation of how accurate GPS is, you would only stay on a road, say, for a minute if you make this correction. Otherwise, you'd go off the road if you do a little calculation. So even something as abstract as general relativity has an effect on our everyday life, which is a justification for what we do. 1 year after Einstein predicted general relativity, or made his theory of general relativity, he wrote a little paper, which I show here, the head of it in German, which is that he predicted that there are waves associated with gravity, just like there are waves associated with electromagnetism. That came about not by a derivation, but by the fact that he looked at the equations in a certain way, and they reminded him, or they looked similar to the equations of electricity and magnetism. And since electricity and magnetism, if you do the equations, has waves, he suggested that gravitation will also have waves. The original paper has a couple of serious mistakes, which he fixed in a paper 2 years later in 1918. And so this is now more than 100 years ago. And in the second paper, he made an important correction, which was the strength of it. Glad he fixed that. But he also told us how you produce gravitational waves. Electromagnetic waves, you might recall, were discovered by Hertz in 1887 by taking two charges and oscillating them, like my fingers. If you see my picture, I don't know if you do, but just oscillating them up and down. Went in the next room, detected that waves came out when there were two charges oscillating toward each other. And then he moved forward and backward toward the source and saw it was wave-like. In the same way, gravitational radiation should do the same thing, but to create the radiation, you don't use a dipole like Hertz does, but a quadrupole. That is something that has 4 poles instead of 2 poles. I'm not going to talk more about that, but then using this, if you have 2 objects going around each other, like as shown in this picture here, this is 2 objects going around each other, and pictorially is showing that it spins away energy in the form of waves, which are gravitational waves. You can see the wave-like structure, and that was what he predicted happens if you have 2 massive objects accelerating around each other. The 2 objects that we detected initially were 2 black holes going around each other. And since that time, we also detected 2 neutron stars around each other. And I'm going to show you a little bit about the second one in a couple minutes. So what is gravitational waves? It's not like electromagnetic waves where there's a photon that goes with it. It's actually ripples in space-time itself. So space itself, you might think of is like a material. We have materials. Materials can be bent, they're straight. They could be in a form of a wave. You can do anything you want with materials. But what does it mean for space to be a material? If you were to use undergraduate or graduate physics and calculate it, it would have a Young's modulus and all the things you do when you have a material. But this material is incredibly stiff. So space technically is very, very stiff. But when the ripples go through it, it stretches and compresses it just a little bit where it passes through. And that's what the waves do. And I'll show you how we try to detect that. The amount is incredibly small. I show that in the little calculation below. The amplitude of the waves is a very tiny number. The little h is a term that comes out of general relativity. It's like the wave function in electromagnetism, and the size of it is got a lot of zeros, 10 to the minus 21. So if I take something that small, the amount that it's going to change space-time, I calculate for you down below. So if I have something 1 meter in size, say a circle of test masses, how much will the circle, excuse me, be distorted? It'll be distorted 1 part in 10 to the 21 meters. So that is how much we have to be able to calculate. We use a technique called interferometry, and I'll just show you in a movie how it works. That is, there's 2 arms, they're nominally the same length. How do we measure that one of them gets a little longer and one of them shorter? By the distortion of space and time. We send light, half of it one direction, half of it the other. If the arms are the same length, they'll come back and exactly cancel each other, as you see here. But if one of the arms gets a little longer than the other because of the distortion of gravitational waves going through, then they won't exactly cancel, and we measure a signal. That can be done incredibly accurately using interferometry, which is what we do. So that's, without talking about it in any more detail, that's what we do. In terms of numbers, what we're trying to see is something like this picture here, which is oscillating for, say, a gravitational wave at a couple times a second. But because the number in the theory is 10 to the minus 21, the size of the distortion is so small that if I do use interferometry, I'm talking about a change of length of the arms that is only 1 part in 10 to the 12th of the wavelength of the laser light that I'm using. And beyond that, there's technical problems. That is, the Earth shakes, and we have to use a technique to reduce the vibrations of the Earth by 1 part in 10 to the 12th, which is incredibly small. I won't go through that technically, but that's why it took so long to make an instrument that was good enough to do gravitational wave detection. I'm going to skip the technical part and show you the detections just a little bit. So we have 2 big interferometers, like I just showed in the picture, one in the northwest corner of the US in Hanford, Washington, and one in the south in Louisiana, in a place called Livingston, Louisiana. If at the speed of light, the time to go between one and the other is 10 milliseconds. So depending on what direction a gravitational wave might come in, if it comes in from the south and goes up, it could take 10 milliseconds earlier in Livingston, or it could come down from the upper left. It would be 10 milliseconds earlier in Hanford than Livingston. So we require that they come at the same time as each other within 10 milliseconds. And then the difference between the 2 helps us point to where they are. This is just a picture of the 2 instruments. They're large. They're 4 kilometers on a side, and they're just very, very, very fancy interferometers. Just to give you a sense of what has to be done technically and what is done without talking about the technologies, an interferometer looks like this. The laser beam comes in and goes down the arms. But if we have air in the arms, there's molecules there. The light scatters against the molecules and won't go in a straight line. So we have to be in very, very high vacuum. Second feature is the laser itself. We all think of a laser, we all use lasers as being incredibly accurate. But we actually have to make them much better than the lasers that you buy. We have to make the frequency much sharper. And we have to make sure the amplitude doesn't fluctuate, and so forth and so on. So there's a lot of very fancy electronics to do that. We have to worry about seismic noise, that is, noise that has to do with the shaking of the Earth itself. And it's one of the most difficult problems because it can move this final mirror and change the distance that we have. And that was a very kind of technical problem, but a very detailed one. We also have mirrors at the ends that are made out of material, and those materials have atoms in them. The atoms move around, and they get warmed up by the laser beam coming in, and so we have something called thermal noise, or if you know it, Brownian motion, and that is also a limitation. And lastly, we have quantum effects. Even we have so much light, and we're measuring things at such small distance that the laser beam puts a pressure on the mirrors, which can move it, and at the same time, you need a lot of photons to be able to detect very accurately. So we have to do something to minimize the quantum noise. I'm not going to talk about any of these technical things today, but just to indicate in a picture, we go from a simple interferometer shown in the upper left-hand corner to a very complex one that we use for LIGO itself. And that's a lecture or a course in itself. In order to get rid of, just to show you one feature, the shaking of the Earth, we have the world's most sensitive shock absorbers. They are shock absorbers like you use in your car, 4 layers of them. But we then, and they're very special, but beyond that, we sense any residual motion actively and push against it. And so this reduces the motion of the Earth in the frequencies that we detect by a factor of 10 to the 12. This is the first detection of gravitational waves. What you're seeing is on the left column, you'll see, if you can read it, where it says strain, the scale is 10 to the minus 21, just what I told you was the size of the effect in the beginning. The scale from left to right is 0.2 of a second. The top trace is the trace in Washington, the bottom one. The middle one is the one in Louisiana. And you see they look like each other. The bottom one, we just put one on top of the other, and you see they look like each other. So that gives us great confidence that we're seeing the same thing in 2 distant places in the US. Then we look in detail at the shapes of what we see. And so what I show here on the right in the top is the same 2 signals. The one on the left is Hanford, Washington. The one on the right is Livingston, Louisiana. The trace in the middle is what we would get if you just take Einstein's equations for general relativity. And you can see they pretty much almost look to the eye the same. And in fact, I can subtract one from the other, and I get this third line, which is just a little shaking up and down. No sign of any shape of anything. It's just the residual noise in the instrument. So that told us, when we used Einstein's equations, that we detected the merger of 2 black holes by the detailed shapes. One of them was 36 times the mass of our sun. The second one, 29 times the mass of our sun. And the final merged object was 62 times the mass of our sun. Notice that 36 plus 29 is 65, not 62. And that just tells you that 3 solar masses, it turned into energy, 3 solar masses, 3 times the mass of our sun, went away in this merger at the speed of light in the form of gravitational waves. And so basically, I just want to show you one more thing and give you a chance to ask me some questions. We basically have seen a different kind of object, which is called a neutron star merger. Neutron star merger has the feature that it can also be seen in telescopes because it emits photons, what are called gamma ray bursts. The picture on the right is just where it was in the sky, seen by us, where it says LIGO Virgo, seen by some satellites, and they overlap each other. And the picture on the left, the vertical line coming up is when we saw the detection of gravitational waves, and the shaking are different instruments from gamma ray observations that shows a signal just 2 seconds after our signal. Why would it be 2 seconds after? Because gravity comes when these 2 objects are coming together. The signal comes afterwards, after they merge. The nuclear physics makes gamma rays. But so that it's expected it'll be later. But the total time is the two signals are within each other within a second or so. And the distance away of this object was 150 million light years. That's 1.5 10 to the 15 seconds. So just looking at this graph, we know that gravity or gravitational waves travels at the same speed as electromagnetic waves, or the speed of light, to within 2 seconds. Within 2 seconds, which is within one part in 10 to the 15. This then, the signal seen by electromagnetic detectors was tracked for days and weeks afterwards, where the first signals that came out were high energy gamma rays. Finally, after weeks, it changes to lower and lower frequency, X-rays, and then eventually radio waves. It's an interesting feature, and that is that sometimes when you do physics, you discover something that has nothing to do with what you are looking for. So yes, we saw neutron stars merge. That's very interesting physics, and it's what we're looking for. But there's another outcome of this, and that is we have had a mystery, even ever since I was a student in physics, explaining how heavy elements got into the Earth. This is a geology issue or a creation of the Earth issue. How did elements, heavy ones like gold, platinum, uranium, get into the Earth? Because our explanation of how elements were made is in the cosmos. We basically make light elements. So most of the universe is hydrogen and helium. If you take then how you get heavy elements, it comes from, we believe, the burning of the stars. So our sun, for example, is burning by the nuclear fusion process, and the elements, first the light ones, and eventually it gets to the heavier and heavier and heavier ones. Starts with hydrogen and helium and oxygen. Eventually it gets to iron, and then the fusion reaction doesn't work anymore. So you can only explain making elements up to iron. Gold and platinum are heavier than iron. So to make them heavier than iron, you need a new mechanism. Well, it turns out that mechanism is probably the one we observed, and that is the collision of two neutron stars. Of course, we saw one now, but the neutron star merger a long, long time ago presumably made the gold, platinum, and so forth that got into the Earth. The one that we saw, we can calculate, produced 100 Earth masses of gold. So, okay, last couple slides, and I'll take questions. Just like in astronomy, where we look at different wavelengths and different frequencies, as I showed on a very early slide, we now are going to begin to do that for gravitational waves. So there'll be a gravitational wave project in space within the next decade. And it'll look for gravitational waves from objects just like we do, but at much lower frequencies. We do on the Earth from 10 hertz to 10,000 hertz, what we call the audio band. LISA, this laser interferometer space array, will do something like 10 to the minus 2 to 10 to the minus 4 hertz. Then there's another detector, which is using natural sources, pulsars, which are very good timing objects, and looking at what happens if a gravitational wave goes through. When you have a field of view of a set of pulsars, it'll change the relative timing, and that looks at yet even lower frequency. So we can look in the future at the possibility that we can do a whole set of frequencies for gravitational waves, just like we have in electromagnetic waves. And I think I'll stop here to give you a chance to ask me any questions. Thank you.
Thank you so much, Dr. Clary, for such a wonderful talk. I'm sure there's a lot of questions. Can I get started with the live audience, please? Is it okay if we go for some questions? Is it okay if we go for some questions?
If you what?
Is it okay? Can we go for some questions now?
Sure.
So thank you for the presentation, Professor. I want to ask, what is the significance of low frequency observation of gravitational wave? And also, in the future, is there a possibility for us to have higher angular resolution for gravitational wave observation? Like we can draw some sky map.
Okay, good. Let me take the second part, which is easiest first, or shorter to answer. The way we get resolution to point is by having several, just like you do in sailing the seas. We use triangulation. So you need detections by several objects that are spaced from each other. On the Earth, we're limited by basically spacing them around the Earth. At present, we don't have a detector, for example, in the Southern Hemisphere. We're building one to go in India, which is as close as we can come, and that'll improve the angular resolution. But we're basically limited by the Earth size at our frequency. In space, we have, I showed you a picture of a triangular set of detectors, and the spatial resolution there depends on how far apart you put them. So basically, we're able to do it, I think, for most astronomical things as well as we need. That's a very interesting question. Your other question is even more interesting because you asked me about low frequency gravitational waves. And in my mind, if we're today like Galileo was in the 1600s, and then you project what's going to happen in astronomy, I think if we do the same thing for what do I think will happen in the next hundreds of years in gravitational waves, I think potentially the most important thing and the most fantastic thing that it'll do is to give us an instrument that can really look at what happened in the early universe. And what we use, how we study the early universe now is what's called the cosmic microwave background. That's looking at, but the problem is that that's electromagnetic interactions, and the universe is opaque below 400,000 years after the Big Bang. So using electromagnetic probes, we can only come toward the Big Bang 400,000 years away. The only two ways that you might get closer to the beginning of the universe is with neutrinos, which could come within a few seconds of the Big Bang if you could detect them, but they're so low in energy that we presently don't have a way to detect them. But the best yet would be gravitational waves, which were created at the very first instance of the Big Bang. But their frequencies were very, very low. So we need to be able to develop the gravitational wave detectors that can get to these very, very low frequencies to detect them. So I think that, and studying the insides of black holes and trying to resolve maybe quantum physics and gravitation, which is another big puzzle in physics, are the two big future potentials that we don't know how to do today at all for gravitational waves. Thanks for the question.
Thank you so much.
Thank you so much. I would like to call for another question.
Okay, so thanks, Professor Barish, for this talk. So I have a question. Before Lemaitre and Hubble, this proved that the universe was expanding. Einstein thought that the universe was static and thus included a cosmological constant in his field equations. So with that being said, how did that affect our understanding of gravitational waves?
Yeah. So your question is really about Einstein's theory and a problem, not about gravitational waves exactly, but let me give you what I can tell you. So we've had this puzzle for about 20 years that we've known that the universe is expanding, and expanding fast. Of course, that's been known for a long time. But what was discovered is not only is it expanding, it's accelerating. And it's hard to imagine when you have all these masses why it would accelerate. It's like there's a negative pressure. We can conceive of negative pressures, but what's a negative pressure? And it may be, and so we don't, that's when we give it a label now, it's called dark energy. So to characterize it by a number, we call it dark energy. But one possibility is that the whole foundation of the way we calculate this, which is based on Einstein's general relativity and curved space-time and all that, it has a problem. And there is one feature, general relativity, if you've studied it, which is there's a constant, the gravitational constant. And Einstein himself questioned if that's really a constant. He thought that might have been his biggest mistake. And so we don't have an alternate theory, but we either presently have to find a theory where that's wrong and that's not a constant, or we measure more features other than the acceleration. And that's the work that's going on to try to characterize what dark energy is. So it's one of the most important problems in physics, and presently we don't have a very good handle on it to solve it. Thank you.
We have time for one more question, maybe.
Thank you for that presentation. Are there experiments planned that can detect quantum effects on gravity?
No. Let me address the question. I wish we did. So the problem, as we know, is that it's embarrassing to be a physicist in some one sense. And that is, we have two wonderful theories of physics, one based on quantum mechanics, one based on relativity, Einstein's theory of general relativity, one based on quantum field theory. The one based on quantum field theory measures, everything we can possibly think of, and very fancy instruments like the CERN particle accelerators. And Einstein's theory is fantastic at doing anything in relativistic astronomy. But it's got to be embarrassing to be a physicist and say that we have two different theories. They have nothing to do with each other. And you apply one here and one there. But that's the situation we're in. So your question is the right one, which is how do we bring these together? We have whole institutes that are working on it theoretically. There's an institute, for example, in Toronto, a center where the theoretical physicists work on various theories, quantum theories, quantum relativity theories. My own view is that what we're lacking is something that we always need in physics, and that is some sort of clues that come from measurements. We just talked about dark energy a minute ago, and the clue there that we have, at least, is that the universe is accelerating as it's expanding. Here, we don't have what are the clues that tell you how to bring together relativity, general relativity, and quantum physics. I can imagine a couple places where we could find clues. We don't have the techniques yet. One would be if we can do experiments inside black holes. So inside black holes, we have to conserve quantum numbers, things that are quantum physics. And of course, we have all the physics of the black hole itself, which is general relativity. We don't know how to go in, so we're barely able to. I showed an image of the surface of a black hole. At the present time, we don't have any way to go inside, but that would be a laboratory if you could, maybe someday, where you could try to reconcile both quantum physics. You're in a regime where you can try to reconcile both quantum physics and relativity. The second, which I think is more likely, but maybe I'm wrong, is what I talked about just with the last question, and that is the very early part of the early universe. In the very early universe, we created particles and energy in quantum physics. And at the same time, that's when we have gravitational waves and the expansion of the universe and relativity. So I think the two possible laboratories, if you want, where you could study and try to get some experimental clues of how to bring these together if we don't somehow in the meantime solve it theoretically, which we haven't been able to, would be experiments in the early universe. In either case, I don't think it's going to happen probably within our lifetimes or within your lifetime, let alone mine. But I think it's possible. So at least I can conceive of ways that you could try to bring them together. Maybe we'll find some ways theoretically in the meantime. Otherwise, I would say it's the biggest embarrassment in being a physicist, the fact that we have two theories of physics and, neither of the twain shall meet. So thank you.
Thank you.
Can we try to fit in one last question, please?
Sure.
Hi, thank you for your presentation. I was just wondering, my name is Karma, when you're detecting these gravitational waves, how do you differentiate between actual signals caused by that and just background inference and like CCIR?
Yeah, that's a good question. How do you know that what we saw wasn't some sort of background? We do is look for signals when the two detectors that we have are in coincidence. They happen at the same time that a gravitational wave would hit them. And when they're not in coincidence, that's background. They're uncorrelated with each other. And so we measure all the times. We measure look for gravitational waves, not just when they're in coincidence, but also all the times when they're out of time with each other. And from that, when we find an event, we compare it with that to tell what the probability is that that's actually an accidental event that happens. But we can do it from our data itself. I don't know if that was clear, but that's okay.
Thank you so much for your time again.
Okay.
Thank you.
Bye-bye.